All right. This question wants to know what the equilibrium pressure is of, we'll go with water to begin with. So now we need to solve. And to do this, we're going to set up our equilibrium constant. So we've got K, and they've given us KPs. So we're working with KPs here. Products. So you've got the partial pressure of CO times the partial pressure of hydrogen gas over the partial pressure of water. We also need to set up our ice chart, and we don't have solids in our ice chart, right? We only have gases or aqueous substances. So I take my initial concentrations. My initial concentrations, 1.24 atm, 1.07 atm, and then hydrogen gas, 1.36. Now, the equilibrium constant for this is 2.44. We have to know which way our reaction is going to go. Are we going to move to the products, or are we going to move to the reactants here, right? That's a valid question. So what we have to do is we have to figure out the value for Q, or a reaction quotient. So when the system is at its initial state, does it have too much product or too much reactant? So we're going to take that initial partial pressure of carbon dioxide, multiply that by that initial partial pressure of my hydrogen gas, and divide that by my initial partial pressure of water. And that's going to give me a value of, getting out my calculator here, fun-filled real-time action here, divided by 1.24, gives me a reaction quotient of 1.17. Therefore, my Q is less than my K, so the reaction is going to indeed proceed to the forward direction, meaning we're going to break down our reactant and make product. So we know that it's going to be minus X, plus X, plus X. So our equilibrium concentrations are going to be 1.24 minus X times 1, and then 1.07 plus X times 1.3 plus X. And now we get to have some fun with algebra. So we've got 2.44 equal to 1.07 plus X times 1.36 plus X divided by 1.24 minus X. All right, and let's continue here. Some algebra is definitely going to be coming into play here. So trying to think the best way to do it. I'm going to bring the bottom term around to each side and then multiply by the top. So we've got 2.44 times 1.24 minus X equals, and then I'm going to FOIL those guys, right? I'm going to FOIL the top line. So I've got 1.07 times 1.36 equals 1.4552. Then I have, what is that going to be? 2? Oh, I like that. 1.42, right? Ah, 4.3. I am mathematically challenged today. I'm going to go ahead and distribute on that side. So we've got 2.44 times 1.24 equals 3.0256 minus 2.44x equals everything on the other side. Now I have to move everything over to the other side. So to do that, I'm going to subtract, I'm going to subtract 3.0256 from this side and add 2.44x to both sides. And that's going to give me x squared plus 4.487. Told you I was mathematically challenged today. And then minus so I have that as my quadratic equation. So now I have to set up my quadratic equation. X equals the opposite of b plus or minus b squared minus 4 AC. That's a 0, not a 6, by the way. Divided by 2a, and that's going to give me, and if you punch that all into your calculator, we are going to get, and I'm going to pause the video here while I calculate this. All right, you get x to be equal to 0.30544, but that's not the end. You then have to take this x value and take it back up to your ice chart. Because according to your ice chart, your equilibrium values are gained by subtracting them from the x from the initial concentration or adding it. So for water here, I'm going to take 1.24, the initial concentration, minus that x value. And that's going to give me 0. Whoops, I can't do a math today. Forgive me. That's going to give me 0.9 0.35 ATM. Then over here, for carbon monoxide, I have to add X, 0.305, 1.375. Then over here, 1.36 plus 0.305, 6561 ATM. And that's that. Beep.